Hello everyone, welcome back to the course. In this lecture, we're going to talk about Bayesian learning and with an example of Bayesian linear regression. So in the previous lectures, we talked about maximalized estimation and MLE. So I just review those criteria briefly. So for MLE, it's a frequentist point of view, okay? Frequentist point of view. So I have a model of how my data is generated parameterized by my weights or by my parameters. So I can, in general, represent my model parameters as theta, okay? So where theta is the parameters. So it's just the W in our previous lectures, but theta seems to be more general, is parameters. So it's unknown, but it's constant, okay? Unknown parameters, okay? There's no repeatable experiments on theta, so you cannot model the probability of theta. There's no probability for theta. So when you do maximalized estimation, you are argmax over all kinds of thetas. You can choose the probability of your data under this theta, okay? So when you think of theta as a random variable, then you can say it's a conditional bar, but it's not necessary. You can think of theta as just a constant, so it's not a condition. But for MAP, it takes the Bayesian interpretation of probabilities. So it says theta is unknown, so it's a random variable. Okay. And for random variable, then I can define my prior on my random variable. Okay, so it's the prior. So you have the right to define your prior. The prior is what is your subjective belief on the parameters before you see anything. Then you still have a model likelihood. You still have a model how your data is generated if you fix the parameter, okay? So you still have the model. So the likelihood is P of theta given theta. So this time theta is the random variable. So this term is the same as this term, except that you have different interpretations for your unknown theta, okay? Then based on prior and likelihood, you can now compute posterior. So posterior is theta given theta. Because theta is a random variable, so I can model its posterior distribution. After you see the data, what is your subjective belief, okay? So it's in fact this term, P theta times PD given theta, okay? So this is the prior, this is the likelihood. So the posterior is proportional to prior times likelihood, okay? Then the estimation criterion is theta MAP is argmax of theta P theta given D, okay? So this is maximize the posterior distribution, so it's called max posterior estimation. Okay, so this is the map. So now we assume we're doing linear regression, and pictorially we can think of it as this. So this is my prior. Okay, so this is my prior. And this is my likelihood. Okay, so I can draw it here. So after you see the data, maybe you get a likelihood of this, okay? So this is your likelihood. And this is your theta, okay? So prior is the distribution of a theta. Likelihood is not the distribution of a theta, but it's still a function of theta, right? Then when you multiply your prior and your likelihood, you get your posterior, okay? So you multiply these two terms together, you get this, okay? But the thing is, here it's not exactly the same, it's proportional. So you lack a constant, which is 1 over probability of D, okay? So if you integrate this area, it's not 1. So you shall scale it, okay? And make the integral, make this region as 1, okay? So now you see the maximalized estimation is this. So this is not x, I mean, this is multiplication. And when you multiply the prime and likelihood, you get the posterior. Okay. So when you do MLE, you get a parameter of this, okay? So this is MLE. And when you do MAP, you get a estimation of this, okay? So you see the prime is indeed regularizing my theta, make it smaller, and it complies with our L2 penalty, right? It's not surprising because we derived that for linear regression for the Gaussian noise with Gaussian prime, you get the L2 penalty for mean square error. Okay. But now the issue is, you remember what is the goal of machine learning? The machine learning can be modeled as a framework like this. I have some training data, then I apply some machine learning algorithm, and then I get a hypothesis, and then I apply the hypothesis to some possibly new data, and then I get a prediction, t hat or y star, okay? And where is my measure of success? My measure of success is solely on t star. So my measure of success depends on t star, depends on your prediction on unseen data. Do we care about edge? No, we don't care about edge, right? Because as long as you can make a good prediction, I don't mind how you get the edge, or I don't mind how many edge you have. So a more natural way or a more orthodox Bayesian interpretation of probability is whenever you have something unknown, it's a random variable. And whenever a random variable is not directly related to a task, it should be integrated out. Okay. So that gives us our Bayesian learning. So the Bayesian learning, the full interpretation of Bayesian probability is anything unknown is a random variable. Okay. Should be integrated out or modularized out if a random variable is not related to my task. It's not directly related to my task, okay? So this is the philosophy of Bayesian decision principle. So when you have something unknown, you can model it as a random variable, and you have some prime, and you adjust your subjective belief based on your observation, which gives you the posterior. Then if you are not asking what that random variable is, then it should be integrated out. So let's assume, what if my posterior is this? Okay. If my posterior is this purple curve, obviously you see if you have the map, you still get this point, and you have no difference when you make a prediction. But we know that theta is unlikely to be less than my map estimation, okay? But it's more likely to be greater than my map estimation, right? But if you do map estimation, then you cannot distinguish this posterior, the purple posterior or the black posterior, right? So the idea is we should integrate things out. So my goal is to model the target, okay, of some unseen data given my data, okay, with some training data, okay. So this is my real task, the real goal of machine learning. But for MLE or MAP, I segment it by 2 parts, okay. I first estimate one particular model. The machine learning algorithm is either by MLE or MAP. And then based on one particular machine learning model, I make a prediction. But Bayesian learning says, okay, the machine learning model is a latent variable, and I shall integrate it out, okay? So it says this should be given by, I may have different models. okay? So this is the joint distribution of your prediction with a specific machine learning model, but I don't care which machine learning model it is, I integrate it out. I consider the overall effect, or I consider the average effect based on the posterior distribution, okay? So I can write it out as saying, okay? So this term is the same as this term because of conditional factorization, right? I first ignored these two random variables. They are the same, okay? So I temporarily ignore that. So the joint distribution of T star theta is P theta times P T star given theta, okay? So the two things happens is one thing happens and the other thing happens conditional on the first thing, okay? But I put X star and D train to the right-hand side bar of every probability distribution, okay? So they're the same. This is because of conditional factorization. Then I say this is equal to T star given theta. So why this line equals that line? The reason is first, for the first term, you see T star is my prediction. Okay, so I lost X star here. T star is my prediction, and my T star is the norm of, you know, X star transpose theta and some epsilon, okay, sigma epsilon square, some noise, okay? And obviously, given my theta, okay, given the parameter, it's independent of your training data, right? Because training data does not appear in this equation, okay, if your theta is given. If your theta is not given, then the theta is a function of your training data. But suppose my training data is given, then it's a not function of your training data. So I can cancel this condition. Okay, am I right? No. So this should be conditional bar. Then the second thing is y theta only depends on D train. It's not a function of X star because it's the unseen data in the test phase or in the prediction phase. Okay, but my theta is estimated or computed based on your training data. So you learn your model based on your training data. So it's not a function of your unseen data. So I can remove that condition. Okay, so this gives me this term. Okay, so this gives me the general principle of Bayesian learning. It basically says, in this posterior, I'm not choosing one particular theta, okay? I'm not choosing one particular theta to predict my target, but for every theta, I have a target, okay? For every theta, you get a target, maybe like this, okay? This is my target. This time it's not theta. And then for another theta, I get another target, okay? And this theta, I get this target. And then I take the weighted average of all theta you have from your posterior. So this gives me the posterior distribution of t given x, okay? But this is for unseen data, okay? And this time theta is not a particular value, but it's integrated out. But theta itself is based on training data, so I can say it's D train. Okay, is that clear? So this is the general principle of Bayesian learning, okay? And you can write out this term a little bit more, and you say this is the same as P theta times P data given D train, given theta, D theta. Then if this is the case, you should write proportional, okay? So it basically says it's this term, this is your ultimate task of the machine learning system. It's known as the predictive density. It's proportional to the integration where you involve the prior, the likelihood times how you make a prediction. Okay. So this is the general principle for Bayesian learning. Then I would like to apply the general framework to a particular machine learning model, which is our good old linear regression model. Then it gives me the Bayesian linear regression model. So this time I have the cheat sheet. It's a very tedious computation, and it's the first time in this course that I have a cheat sheet. Then at some step, I will show the equation without calculation. Okay, you know, I'm very bad at math. I'm very slow in calculation, so I will give the result without calculating it. So by doing Bayesian learning, you know, again, you need to have the assumption of your likelihood, have the assumption of your prior, and then you compute the posterior as if in the map estimation, okay? But instead of taking one particular model, you are integrating over all kinds of models. So this is the difference. So I assume in Bayesian linear regression, I assume my data is indeed generated by, linear regression model where the T target is W transpose X. Okay. Okay. Then for computational convenience, I can write this in a vector form. Is normal of X W. It computes the mean for every sample at the same time by one matrix vector multiplication. Then I denote the covariance matrix by lambda. Okay, so lambda is just a sigma epsilon square up to sigma epsilon square diagonal matrix. Okay. It's the same as my MLE estimation, except that I just represent it by the vector form. Okay, it's more convenient. So this is my likelihood, how my data is generated. Then I also assume the prior, assume my prior W. Now it's a vector. It's generated by Gaussian. Okay. Okay. So I model all the weights at the same time, so it gives the high dimensional Gaussian, and then the mean is the M0. In our MAP, I just know that M0 is a zero vector, and S0 is just the variance, it's the diagonal matrix of epsilon W square up to epsilon W square. Okay. Why I call it W0 and S0? Because it's the mean and the covariance matrix before you see any data. So it's the mean and covariance matrix, you see 0 data samples. Okay, so it's called M0 and S0. And when you see more and more samples, you will adjust it and you will call it MN and SN. Okay, so this is the notation here. Then I can do the posterior. So now I compute P of W posterior. So this is the prior, and this is the likelihood. Now I compute the posterior. Okay. So this is your assumption. The likelihood is also your assumption. But after you assume the likelihood and the prior, then you don't have the privilege to assume the posterior again. Okay, it's just computed. So the posterior P of W given your training data is proportional to P of W times P of T given W. right? So it's proportional to, so I can drop the 1/2 pi stuff, okay? I just drop the constant because I say it's proportional, and it's proportional in terms of my W, okay? So it's actually exponential of 1/2. Where's my W? W is here, right? So it's W minus M naught transpose S0 inverse W minus M naught times exponential of this term. I don't have enough space. T minus W transpose, this term, sorry. I'm doing the vector notation. So it's the T minus XW transpose lambda inverse T minus W XW, okay? So by completing the square, I know this term is definitely a quadratic term, right? If you have the exponential times the exponential, then you can make one exponential and the term here adds up, right? Okay, so now you see this term is quadratic, okay? The first term is quadratic, and the second term is also quadratic. And you have the insight that if you have two quadratic terms, then it's at most quadratic. So shall I compute the term? I can show you the quadratic term itself, okay? So the first term is W transpose S0 inverse W plus the term here is, so I have 1/2 here, okay? The term here is this, okay? It's W transpose X transpose lambda inverse X W, okay? Then I can say this is half W transpose S inverse plus X transpose lambda inverse X, okay? Now I assume lambda is this term, so I can say this term is 1/sigma squared, okay? And W, okay? So this is the quadratic term, and then you have the linear term, and then you have some constant regardless of your W, right? So now you can do the completing the square, and you will say this is equivalent to, it's proportional to some W minus M naught M N transpose S N inverse W minus MN, okay? For some MN SN, right? So here I just show how you compute the quadratic term, then you still have a linear term and you have a constant term. And the constant term can be ignored because when it takes out of the exponential, right? You takes out of the exponential, it becomes a multiplicative factor, and then it's proportional. So I just ignore that. Then you can compute the square. You say this is the quadratic, this is the linear term. Then there must be some mean and the covariance make it the same, okay, right? So now I'm cheating. So I'm going to tell you this term is this. Okay. So this shows that the posterior of W is a Gaussian, which is not surprising. And then its mean after seeing n samples is this term, and after seeing n samples, the covariance matrix is this term, okay? So these two terms look scary, but everything is just the input or your prior, so it's computable, okay? So even if it's a very long equation, when you type into, for example, Python, it's just a one line of code. So all of the things are computable, then it gives me the posterior of W, which is a Gaussian. Then the next step is predictive density, which is my goal of machine learning. Predictive density is P of T star given some new data X star, okay? With my training data is the integration of Px star given T star and theta, okay, times P or W. PW given D train. Okay. But I integrate out my W. So now you see this gives me a Gaussian, so I don't want to write it out. So this gives me a Gaussian, which is T star, okay. X. The mean is X transpose, X star transpose W, and the covariance matrix is what? It's S0, no, Sn, okay. No, it's lambda. And this term is the Gaussian of W with mean being Mn and the covariance matrix Sn Tw. Okay. So without computing anything, I know this is a Gaussian. So here I'm just talking about one particular data sample. So it's a univariate Gaussian with mean mu star and standard deviation sigma star. The reason is this is a Gaussian and this is another Gaussian. So you can think of it as a Gaussian distribution times the conditional Gaussian, okay? The T given W is still a Gaussian. Then Gaussian times the conditional Gaussian is a joint Gaussian, okay? And then you modularize out W, so modularization of your Gaussian is still a Gaussian. So it's just a Gaussian, right? And here it's similar to a Gaussian times a Gaussian, now you get another Gaussian, right? So you think of Gaussian distributions. So you think of Gaussian distributions. So when you do conditional, it's a Gaussian. When you do modular, it's also a Gaussian. And when you multiply two Gaussians, it's again a Gaussian. So everything is a Gaussian. So now I'm cheating again. So I'm just going to write out the mean and variance without computing it. It requires some calculation and some identities of inverse. So I just write it out. So the calculus is very tedious, but the result is just a Gaussian. And we notice that for Bayesian linear regression, if your prior is a zero mean, okay, prior is zero mean, and if your target is contaminated by some noise, you know, which is also zero mean, but other than that, it's a linear model. So it's basically the assumption of linear model. Then it gives me the target, you know, it's a distribution, okay? It's a target. It gives me a distribution. P T star given X star D train. This is my predictive density. And surprisingly, the mean, the peak of this predictive density is the same as map, okay? So for point estimate, the Bayesian linear regression model is the same as map, okay, with some, you know, normal assumptions. Okay, the result is the same. This is just my map, okay, the closed form solution of my map. So this is my MN, okay, which is my map estimate. And when you do a prediction, you just multiply by that. It just gives you the same prediction as map, okay? So this shows Bayesian linear regression with these assumptions. The most probable target or the peak of the target is the same as map. So why do we bother doing Bayesian learning? Why Bayesian learning? Okay. First, it gives me some modeling of uncertainty. Okay. For example, if I have a linear regression model and, you know, my data are almost there, then, you know, if you have the map estimate or MOD estimate, you are doing a point estimate of a target given your input, right? So you just get a line, and you don't know whether your prediction is good or not, whether you have confidence in your prediction. You have no information about that. But if you model it in a Bayesian way, then you know here my standard deviation or my variance is small. The predictive density, the variance in your predictive density is small, okay? The sigma star is small. So, you know, then you are very confident. Then if you going a little bit out, you know, the variance becomes larger and larger. So even if I have the same prediction as the map, I know here the confidence level is low, okay? And when you buy some stock, of course, if you predict here, then you don't probably buy it. But if you predict here with a very small variance, you probably trust your prediction, right? Or maybe you can do active learning. If you see some new data here, then you make a prediction with a very small variance, then okay, it's good. I have a high confidence that I predicted correctly. But now what if you see a data and now my predictive density has a large standard deviation, then you say it's very uncertain. Suppose you can ask humans to annotate your data, then this is a much more effective sample than this sample, right? So you can do active learning. And the other thing is you can do online learning. Okay, so you have the prior, then after you see a few samples, you have the posterior. But then you observe more data, your previous posterior becomes the prior, and now you can recompute the posterior, right? So this is the online learning. And in this case, we typically work with the conjugate prior because the posterior and the prior have the same format, right? And then after you observe more and more data, you just update with your posterior. Then before you observe new data, it's your prior, right? And then if you really observe more data, then you can update your posterior. So this is something known as online learning. If you have a well-defined prior or you really believe in your prior, then with Bayesian learning, you know how much you should adjust based on new observation. Okay, so this is different from, for example, a gradient-based method or maybe pre-training, and then you first train on the first few samples, then you train on another few samples. You don't know how many updates you should have for the new samples, but in the Bayesian learning, you know how much you should adjust based on the new samples. Okay, so this is another advantage of Bayesian learning. But the disadvantage is, of course, it's very it's computationally intractable. Okay, so you see for Bayesian linear regression, the computation is already very tedious. And if we have a more complex model, for example, if we have the linear classifier, or known as the logistic regression, then we don't have a closed form solution for that. So now you have some approximation or you do some sampling to compute the expectation. then it's inefficient. Okay. And another issue is, in Bayesian learning, you don't really have a overfitting or underfitting because you do have your prior, and then you have some observation. You can indeed compute your posterior, but the issue is maybe your prior is incorrect. Then it gives you a bad prediction. Okay, so it's subjective. So how can we choose prior? Okay. So let's assume we have some theta. Okay, so based on my theta, I generated my data, right? This is what we have. So I denoted by a directed graph where an edge just means based on something, I generate some other things, okay? So we have theta. In this case, it's from a normal distribution with zero mean and standard deviation. I call it lambda squared, okay? And my data is, for example, I say my t. So I have t. I model my data as t, okay? So my t is theta transpose x plus some epsilon, then it's actually okay. The question is, how can we choose lambda? Okay. So first approach by grid search, or by line search or grid search, depending on how many lambdas you have, okay, by validation. If you do validation, then it's not the orthodox Bayesian learning, because Bayesian learning says, what is your prior? If you really believe that, then I give you the best prediction that you can have. This is the conditional Bayesian decision principle. But the issue is, I don't know whether I truly believe this or not, okay? So this is my validation. So you can do it by validation of line search or grid search, okay? Depending on how many variables. But is there any other approach? So in this case, I can say T is generated by PT parameterized given by theta, and theta is some distribution, okay? Given by lambda. So, in the Bayesian interpretation, everything unknown is a random variable. So now I can model lambda as a random variable, okay? So lambda is generated from some P lambda. Okay, now things becomes interesting. So I say, this is my lambda. Lambda is a random variable, okay? It has a prior, for example, lambda is standard norm. I don't even have a variable here. And based on my lambda, I generate my theta. And based on my theta, I generate my data, okay? And I can do Bayesian learning. By doing Bayesian learning, I actually integrate out my theta, okay? So in this equation, this is your predictive density. You don't have theta, right? You only have your lambda, okay? So if you eliminate your theta by marginalization, then I can say, okay, I can say, this, okay? And you just remember that it's not too different from my previous diagram. I just drew it here, right? So this is my data. So they're just the same, okay? They're just equivalent, you see? Originally, you have theta generates t. And now I do some Bayesian learning, and then I have some prior for my prior. And then I blame theta as lambda, right? Now I have lambda, then I generate t. So how can I do the estimation for lambda? considering that you have multiple lambdas, now grid search or line search is not feasible. How can I do that? So how can I estimate lambda? What you have learned for estimate theta cannot be applied to estimating lambda because they have the same topology. So I would say lambda hat MLD is the argmax over all kinds of lambdas that you can choose P of T given lambda, okay? Or parameterized by lambda, I don't mind. So this is essentially argmax over lambda. I first generate theta, okay, T, so I don't want to write too many steps, but it's just based on my lambda, I generate theta, and then based on my theta, I generate T, but I don't care about theta, so I integrate out, okay? So this is the maximalized estimation for lambda, but this is the Bayesian learning for theta. So this is known as the ML2 or the type 2 maximalized estimation, type 2 ML, okay? Similarly, you can say map 2, okay, type 2 MAP, where you define a prior for lambda, okay? So I would say MAP for my lambda is argmax lambda. So this is, I mean, parameterized by lambda is actually a conditional bar. So now this is T comma lambda, okay, the joint distribution or the posterior distribution. Actually, I can write it as P lambda given T, okay? And this is actually P, I first generate lambda, then I generate theta given lambda, then I generate T given theta, okay, d theta. Okay, because I don't care about theta. So this gives me my MAP. Then I can do Bayesian learning for lambda, okay? Bayesian learning for lambda. So, I mean, in Bayesian learning, you know, what is the task of machine learning? The task of machine learning is to make a prediction, okay? So lambda is something unknown, so it's a random variable. Is this random variable directly related to a task? No, the task is to query about T, okay? But this is lambda in the middle or in previous steps, so I should integrate out. So now my predictive density is P of T star given X star D train. So it gives me P T star lambda theta given X star D train, but we don't care about lambda or theta. None is my focus, okay? And this is given by P T star given my lambda theta times P lambda theta given D train. Okay. Okay, something like this. And you know this is proportional. This term is proportional to P lambda theta D train, which is my equals P lambda times P theta given lambda times P of D train given theta, okay? So now you know how to expand it. And I haven't defined what is my model, so these terms are not computed, but once you define the model, you can actually compute it, although it may be extremely inefficient, okay? So this is known as the full Bayesian treatment. And actually, you know, you can think of what if my lambda still have a the distribution of lambda is not 1, okay? It's still subject to either, right? So now I can do it for another either as my phi distribution for the phi of the phi, okay? So now you see I can define the hierarchical Bayes, and actually nobody do it, it's mostly enough, okay? So for lambda, we typically just set the most intuitive distribution or some non-informative distribution like just 1, okay? Standard norm. Actually, a hierarchical Bayes is not a different paradigm of Bayesian learning. It's just another expression of my prior, because in this model, if you eliminate theta, then you get this model, right? You get this model. But what if I eliminate my lambda, right? Then I can say P of theta is P of lambda times P of lambda given, theta given lambda, but I integrate out my lambda, okay? So now this time, this gives me a prior of my theta, right? So if I eliminate my lambda, then it gives me a prior, then theta. Then I can just use this prior of theta to define a usual Bayesian learning, okay, like this, okay? So a hierarchical Bayes is just a convenient way to interpret your prior, and sometimes it's more robust than you define the prior of theta by yourself. But it turns out that it's equivalent to Bayesian learning. Okay, just review a little bit. So first we reviewed MLE and MAP, okay? So my theta MLE, I just write it again, is P argmax of P data given theta, okay? And then my prediction T star is theta hat, okay, times X star transpose. MAP is the same, okay? MAP is argmax P theta given data, okay? And the prediction is the same, okay? But just different point estimate. Then we talk about Bayesian learning, where we don't care about a particular theta, but we care about the predictive density PT star given X star D train is in fact the integral of my P theta, okay, T star given theta and X star times P of theta given my D train. D theta, but I don't care about D theta. This term, is proportional to P theta times P D train given my theta, right? But the question is, what is P theta? In the Bayesian learning, in this level, you are thinking of P theta is known or it's a fixed distribution, but maybe it's also parameterized. Then you can do MLD, okay? ML2, okay? The type 2 maximalized estimation, which says theta is generated by P theta given lambda, okay? And now this time I can say my lambda MLD is argmax P data given lambda, okay, which is an integration over my theta. And likewise, you can also have the MAP2 and the 4 Bayes, okay? And you can define a hierarchy, but we stop here, okay? And this is known as the empirical Bayes. Or I'm not sure whether maybe MAP2 is also known as the empirical Bayes. It basically says, you have a point estimate of the parameters of your prior, and the 4 Bayes or the 4 Bayesian treatment says you should also integrate out the prior of the prior. Okay, then we stop here, we don't continue. Okay, good. That's it for this lecture, and that is pretty much for linear regression. And we have discussed a lot of principles for machine learning. And in the second half of this course, we're going to talk about classification. And I guess we will proceed much more quickly than what we have done here. Okay, thanks.